If all of this is true, I mean from black holes that can evaporate over trillions of years, to fungi right here on Earth that can take control of an ant's mind, what does it say about who we really are? What does it say about how much we still don't understand about the universe? I've been thinking about it a lot lately. The way the universe, well, the way it's expanding. I mean, we used to think it was slowing down, right? And that made sense. You have this huge explosion at the beginning, the big bang, and everything is just, flying apart. But gravity is always pulling. So you'd expect it to pull everything back in slowing it down like a ball thrown into the air that eventually slows down and falls back. That was the prediction for decades. But then we looked closer. We looked at distant galaxies and they were moving away from us faster than the ones closer to us. Not just faster, they were accelerating. It's not what we thought, not at all, and that was shocking. I think the moment that really changed everything was when we started measuring the light from distant supernovae, exploding stars. You know these specific kinds of explosions? They act like cosmic lighthouses. They always explode with roughly the same predictable brightness, so we can use them to measure distance. If you know how bright something should be and you see how dim it appears, you know how far away it is. And when astronomers looked back in the late 90s, they found that those distant supernovae were dimmer than expected. Dimmer meant they were farther away than they should have been, and that meant the universe was expanding faster now than it was in the past. It was speeding up. And that it doesn't fit. It doesn't fit with anything we had before. So we had to call it something. We called it dark energy. It's just a placeholder, really, a label for our ignorance. But whatever it is, it seems to make up. What is it now? About 68% of the entire universe. Nearly 2/3. So most of what exists is something we don't understand. And the weirdest thing is, it's not like this stuff is pushing things apart directly like some explosion. No, it's built into the very fabric of space itself. Like every cubic meter of empty space has a little bit of this energy. And as space expands, you get more space, which means more dark energy, which means more expansion. It feeds itself. That's really strange. It's like the universe is creating its own fuel for expansion out of nothing. Einstein actually predicted something like this, He added what he called the cosmological constant to his equations. It was a sort of fudge factor, really. He did it because at the time, everyone, including him, wanted the universe to be static. He didn't like the idea of it expanding or contracting. But later, after Edwin Hubble showed that the universe was expanding, Einstein called it his greatest mistake. But maybe it wasn't. Maybe it was right all along, or at least pointing to something real, because now we're back to something very much like it. The equations of general relativity still work, they're beautiful, but to make them fit what we observe, we have to add this extra term, this outward push, but we don't know what's causing it. And then there's the other part of it, the bit that gets to me really. If it's true, if this dark energy is constant, or worse, if it's increasing over time, then we're heading towards a very strange future. Some call it the heat death of the universe, or maybe the Big Rip, depending on the details. You see, if this accelerated expansion continues, then eventually galaxies will drift so far apart we won't be able to see them anymore. The light from them will be stretched so much it will never reach us. One by one, the lights will go out, stars will burn out, black holes will evaporate, very, very slowly but still. And what we'll be left with is just cold emptiness, a dark, dead universe. It's a long, long time away, don't worry. Billions, trillions of years. But still, it's unsettling, isn't it? And I think about how even now, right now, we only see a fraction of what exists. There's a kind of horizon called the cosmic light horizon. It's a boundary beyond which we can't see, not because there's nothing there, but because light from those regions hasn't had time to reach us since the beginning of the universe. So we live in this observable bubble, but outside it the universe could go on forever, or not. It might be finite curved back on itself, we just don't know. And the part we can see, that's not as simple as it sounds, because the universe isn't expanding into space. It's not like galaxies are flying through a pre-existing empty room. No, the space itself is stretching. It's like dots on a balloon. As you blow the balloon up, the dots move away from each other, but they're not moving on the balloon. The surface itself is growing. That's what the universe is doing. This brings up something even more abstract. We're not even sure if this expansion is the same everywhere. Some models suggest there could be other pocket universes, entire domains of reality that never touch ours. That's where the idea of the multiverse comes in, and dark energy might be a clue. And then there's the quantum stuff. Because when we try to calculate the energy of empty space, the vacuum energy, using our best quantum theories, we get a number that is absurdly high. It's like 10 to the power of 120 times higher than what we observe. That's the most wrong any calculation has ever been in the history of physics, which means either our theory is completely broken or there's something huge, something fundamental that we're missing. And there's a chance, just a chance, that what we see as dark energy isn't even a constant. It might vary over time. Some models call this quintessence, which is a lovely word, isn't it, quintessence, like the fifth element. If it varies, it might fade away someday, or it might ramp up, leading to that big rip I mentioned where the expansion becomes so extreme that galaxies, stars, planets, even atoms are torn apart. That's wild, but it's on the table. It hasn't been ruled out. And I think what all of this shows is that we're still so early in the story. We've only just begun to grasp how strange and beautiful the universe really is. 100 years ago, we didn't even know other galaxies existed. We thought the Milky Way was the whole thing. Now we know there are maybe 2 trillion galaxies out there, and most of what makes up all of that is something we can't even name properly. We call it dark energy. But that's just a signpost. A label like here be dragons on an old map when you haven't explored the territory yet. So yeah, the universe is expanding faster than we can explain, and maybe that's a good thing. Maybe that's the invitation, to keep asking questions, to look deeper. What always gets me, is the scale of it. Not just the expansion, but the actual stuff, the stars themselves. I mean, we say things like countless stars or infinite galaxies, but those are just words. They're metaphors, really. Because when you try to quantify it, when you actually count, you get to this number that's so far beyond what we can imagine that it might as well be infinite. You've heard it, I'm sure, that there are more stars in the observable universe than there are grains of sand on all the beaches on Earth. And I remember when I first heard that, I thought, no, that can't be right. Because you can hold a handful of sand just from one beach, and there are, thousands of grains in your palm. Millions. And there are thousands of beaches, thousands of coastlines. How could there possibly be more stars? But then you look into it, you look at the data. There's something like 2 trillion galaxies in the observable universe. That's the current estimate. 2 trillion. That's 2,000 billion. And each of those galaxies, our Milky Way, is pretty average. Each one has hundreds of billions of stars. So even if you lowball it, even if you round everything down, you still end up with a number like 10,000 billion. That's a 1 followed by 22 zeros. It's a number that's meaningless to us, really. We can write it down, but we can't feel it. And what's wild is that every single one of those is a sun like ours. Or maybe bigger, maybe smaller, maybe weirder. Some of them are giants, absolute monsters, burning so hot and so bright they make our sun look like a candle. Others are cold, dim embers, barely holding on to the last bits of fuel. And most of them have what? Most of them have planets. We didn't know that for a long time. We assumed it, I guess. We hoped, but we didn't have the data. And then we started seeing the dips in light. Little blips as a planet passed in front of its star. We saw the tiny wobbles as a planet's gravity pulled on its sun. And suddenly, we realized planets are everywhere. So now we think that there are probably more planets than stars, probably a few trillion of them. And among those, there must be some that are like Earth. Same size, same distance from their star, maybe with atmospheres, maybe with oceans. Statistically, it would be strange if there weren't. And that's the question, isn't it? If there are so many stars, and so many planets, and so much time, where is everyone? That's the Fermi paradox. Of course, you've heard of it, but it hits differently when you really consider the scale. Because the distances are vast, yes, but so is the time. Some of those stars are billions of years older than our sun, which means their planets had a head start, a huge one. They could have evolved life, civilizations, long before we ever existed, long before Earth even formed. And yet, silence. No signals, no tones, no anything. And maybe it's just because the light or the signal or whatever it is, maybe it hasn't reached us yet. The universe is just too big. Or maybe it came and went before we even had radios to listen. Maybe they were here 1 million years ago, looked around and moved on. Or, and this is the dark version of it, maybe there's something about intelligence that always ends badly. Maybe civilizations always reach a point where they burn out. They discover things they can't handle. They destroy themselves before they can ever leave a permanent mark on the galaxy. The more optimistic version is that they're out there, but they don't want to interfere, or they don't care, or maybe we're just not interesting enough yet. But when you stand back, when you look at a night sky, especially far from the cities, far from the light pollution, and you just look, you're seeing something else. You're seeing something ancient. You're not looking at stars as they are now. You're seeing them as they were. The light, it left them maybe 10 years ago, maybe 100, maybe 1,000, maybe 1,000,000. And it traveled through empty space all that time just to reach your eye at this exact moment. It's like looking back in time. Every night, sky's a history lesson. The light from our sun, it takes about 8 minutes to reach us. So if the sun were to just vanish, we wouldn't know about it for 8 minutes. We'd still be in daylight feeling the warmth for 8 full minutes after it was already gone. Now apply that to the stars. The very nearest star, Proxima Centauri, is over 4 light years away. The light you see from it tonight, that light left the star 4 years ago. It's light from the past. You look up at the Orion Nebula, that hazy patch of light, that stellar nursery just below Orion's belt. The light from that region, it left over 1,000 years ago. That's older than most cities, older than most languages in their current form. That light was already on its way when people on Earth were building castles, or sailing on wooden ships, or just looking up at the exact same sky wondering. And some of the stars you see, they might not even exist anymore. They might have died while that light was still on its way. They could have exploded or collapsed into a black hole 1,000 years ago, and we wouldn't know. Not yet. We're still seeing the light from before the end. The sky, it's full of ghosts, beautiful shining ghosts. And the thing is, those stars, that light, they're not just scenery, they're not just distant decorations. They were furnaces. They spent their lives doing something incredible. They took the simplest element, hydrogen, and under immense pressure in their cores they fused it. They crushed it into helium, and then, in the bigger stars, they fused helium into carbon, and carbon into oxygen, and all the way up to iron. All the elements that make up, well, us. When those stars reached the end of their lives, especially the massive ones, they didn't just fade away, they exploded in a supernova, an explosion so bright it can outshine an entire galaxy for a few weeks. And in that final violent moment, they scattered that material, all those heavy elements they had created, they scattered it all across space. And that dust, that stardust, over billions of years, it gathered together. Pulled by gravity, it formed new clouds, and from those clouds, new stars and new planets. And eventually, here we are. Every atom in your body that isn't hydrogen was made inside a star. Think about that just for a moment. You're literally a being. Made of stardust. And it's not just a poetic phrase, it's physics, it's biology. The iron in your blood that carries oxygen to your brain, that iron was forged in the heart of a dying star billions of years ago. The calcium in your bones, the oxygen you're breathing right now, all of it forged in stellar cores, and when those stars died, they gave it all back. That's what supernovae do. They return the heavy elements to the cosmos. It's a cycle, life from death, over and over. And that means that everything we know, everything we build, everything we feel, everything we are, is part of a much bigger process, something ancient and ongoing. And that gives me a strange kind of comfort, because it means we belong here. Not just on this planet, but in the cosmos. We're not separate from it. We're not just observers looking in from the outside. We're participants. We are, in a very real way, we are the universe, becoming aware of itself. And I think that's why we look up. That's why we wonder. That's why we build telescopes and launch probes and scan the sky for signals. Because somewhere, deep down, we know that we're part of that story. That those stars, all those trillions upon trillions of them, they're not just distant suns. They're family, ancestry, relatives scattered across the fabric of space. And the next time you look up, try to pick one, just one little point of light. That light has been traveling uninterrupted for longer than any civilization has existed, and you are catching it. At that one perfect moment, you're intercepting history. And that star, it might have planets, it might have oceans, it might have something looking back. Or It might just be a sphere of plasma in the corner of the galaxy that no one will ever visit. But it's real, and it's there, and we're still learning. Every year, we find more stars, more galaxies, more surprises. The James Webb Space Telescope, for example. That new telescope, it's been sending back images that are, well, they're changing everything. Again, it's been looking so far away, which means so far back in time, looking at the very first galaxies. And it's finding galaxies that are too big, too bright, too developed. Galaxies that, according to our models, they shouldn't be there that early, but they are. And that means maybe our models of galaxy formation are wrong, or just incomplete, or there's something else going on. Again, it's that same pattern. The universe refusing to behave, refusing to fit into our neat little boxes. But that's good. That's how science works. Every new surprise is a clue, a puzzle piece. And we put it on the table with all the others, and we just try to see the bigger picture. Sometimes the pieces don't fit, and we have to change the puzzle. But that's the joy of it. That's the process. And the more we learn, the more we realize just how little we know. Every answer opens 10 new questions, and we keep going. Not because we think we'll find all the answers, but because the questions themselves are beautiful. Because just asking, just wondering, connects us to something vast and timeless and astonishing. And maybe, just maybe, out there, orbiting one of those countless stars is another creature, another mind doing the same thing, wondering, looking up, trying to understand. It's strange, isn't it? How we walk around with this thing inside our heads, this brain, and we still don't really know how it works. I mean, we've mapped it, we've scanned it, we've cut it into slices and labelled all the parts, and yet we still don't know, not properly, what most of it is actually doing. It's like owning the most powerful, the most complex machine in the known universe, and not having the manual, not even knowing where the on switch really is. You just wake up one day and it's running. And when I say it's powerful, I mean properly powerful. Not in the way a computer is powerful, not just with numbers. It's powerful in its complexity. The numbers, I mean, they're staggering. There are about 86 billion neurons in the average human brain. 86 billion. And each one, connects to thousands of others. So we're talking about something like 100 trillion connections, 100 trillion little synaptic bridges, constantly sparking, constantly shifting. It's not a static thing either. It's not a finished product. It's changing all the time. And the efficiency, that's what's astonishing. The whole thing, this entire universe of thought and feeling and memory, it runs on about 20 watts of power, less than a dim light bulb. A supercomputer, trying to do anything remotely similar in complexity, would need what megawatts a power plant, the human brain. It does it on a banana and a glass of water, and it doesn't stop. Not until the very end. Even when you're asleep, it's running simulations, it's sorting memories, it's doing whatever dreams are. No one's really sure about that either. Why do we dream? Some people think it's memory consolidation, the brain tidying up the day, filing things away. Others think it's a kind of internal debugging system, a way to practice for threats without any of the danger. But maybe it's neither. Maybe it's something we haven't even thought of yet. And the thing is, the part of it, the part you're aware of, the part you think of as you, the voice, the consciousness, that's just the tiniest sliver. It's the bit of the iceberg above the water. There's this whole seething mass of neurons firing beneath the surface, doing things you don't even know are being done. It's running millions of background processes all the time. Your heart rate, your temperature, your digestion, your posture, your balance, and it still has spare capacity to let you daydream, or write a poem, or regret something you said 15 years ago. All of that constantly. It's like you're not the driver of the car. You're just the person being told what route you're already on, and it's always changing. Every experience you have, every sound, every conversation, every mistake, it all rewires you. Just a little. You're not the same person neurologically that you were yesterday. That's not a metaphor, that's just biology. We've tried to replicate it, we've built artificial neural networks with layers and weights and all that. And Yeah, they can recognize cats in photos, they can generate a passable imitation of human language, but they're still nothing like the real thing. They don't feel, they don't reflect, they don't suffer, and they don't understand. Not really, not the way we do. Because understanding, that's hard to define. It's not just knowing facts, it's something deeper. Something about being able to model the world, to anticipate, to reflect on your own thinking. And that seems to arise from complexity, yes, but also from embodiment, from being in a body, from having senses and emotions and fears and desires. And we don't fully know how that all links together. We've got regions, right, like the amygdala, that's fear, the hippocampus, memory, the frontal lobes, decision-making. But these are just labels. The activity, it spreads across networks, across multiple areas. And those areas, they change depending on the context. And we're just scratching the surface. We still don't know how memory actually works, not really. We've got models, yes, we've got these ideas about synaptic plasticity, about long-term potentiation, but ask anyone, ask a neuroscientist. Where is a specific memory stored, like your first day at school, or the smell of your grandmother's kitchen? And they'll tell you, we don't know. It's not stored like a file on a hard drive. It's not in one place. It's distributed, fragmented, contextual. You remember something because of the emotional state you were in when it happened, or because something triggered it. A smell, a sound, a face, and consciousness. Well, don't even get me started on consciousness. What is it? Where is it? Is it just an emergent property, just a side effect of all this complex computation, or is there something special about it, something irreducible? People have tried to define it. Awareness of awareness, the ability to reflect, but no one has pinned it down, not properly. You can't point to a single neuron and say, that one, that's where consciousness lives. It doesn't work like that. It's probably more like a process, a symphony, a constantly shifting harmony of electrical and chemical signals. And the strange part, we don't know why it's useful. Evolution. It doesn't really need consciousness to solve problems. Most animals solve very complex problems without, it seems, being aware of themselves doing it. So why did it evolve? Why do we have this internal theatre? And that's the other thing, language. Because the brain, for all its complexity, didn't come with language pre-installed. That's something you learn. And once you have it, once you can use symbols and syntax and metaphors, suddenly you can think in new ways, you can plan, you can imagine, you can remember things that never even happened. Language changed the brain, it rewired us. It created new loops of feedback, thinking about thinking, naming emotions, creating identities, and we still don't know how that leap happened. How a bunch of neurons firing could give rise to Shakespeare, to laughter, to guilt. How thought emerges from matter. How the cold logic of chemistry gives rise to the warmth of feeling. And we're not there yet, not even close. But we keep asking, we keep scanning, modelling, hypothesizing, because if we ever do understand it, if we ever truly unlock how the mind works, well, then I think we'll understand something deeper, something about who we are, something about what it means to be conscious, to be alive, to be human. We have journeyed so far, haven't we? We've drifted through the silent, empty oceans between galaxies. We've watched stars be born in swirling clouds of gas and dust, and we've seen them grow old and return their ashes to the cosmos. We've looked for planets for water, for the possibility of life. And now, after all that looking out there, let's turn our gaze inward. Let's look into the very thing that is doing the looking. Let's think about you. When you think of yourself, you probably think of a single person, one mind, one body, one consciousness. The word I am listening, I am breathing, I am thinking. It feels so solid, so certain, but the universe in its infinite wisdom and its love of strange truths tells a different story. The deeper we look, the more we realize that this feeling of being a single separate I might be the most beautiful illusion of all. The truth is, you are not one, you're a multitude, you're a we. Let's start with the very atoms that build you. Every piece of you, every tiny building block was made somewhere else long ago. The carbon that forms the backbone of your cells, the oxygen you're breathing right now, the iron in your blood that carries that oxygen, none of it started here. It was all forged in the unimaginably hot, pressurized hearts of stars that lived and died billions of years before our Earth was even a speck of dust. You are a collection of ancient stardust. You are a gathering of atoms that have traveled across light years and through eons of time just to come together for a little while to be you. You are not a fortress separate from the world. You're a crossroads. You're a temporary pattern, a dance of matter that the universe is performing. The cosmos is not just something you look at. It is something you are. You are quite literally the universe becoming aware of itself. That's the first many. You are a crowd of countless ancient stars. But let's look closer. Let's look at the life that makes you. If we were to zoom in past your skin, past your cells, we would find a world teeming with life, an ecosystem so vast and complex it rivals a rainforest. You are not a single organism. You are a walking planet. Living inside your gut, on your skin, in your mouth are trillions, truly trillions of other living things. Bacteria, fungi, viruses, and archaea. Most people hear bacteria and think of being sick, but these are your partners. They're your oldest companions. In fact, there are more of their cells in and on your body than your cells. There is more of their genetic information, their DNA, than your DNA. They are not invaders, they are essential. They help you digest your food, they create vitamins you can't make on your own. They train your immune system, and they even help regulate your mood. They are part of you. So when you say I am hungry or I feel happy, who is actually speaking? Is it just the human part, or is it the entire ecosystem, the many, all speaking with one voice? You are not an individual, you're a symphony. You're a collaboration between your human cells and this vast ancient world of tiny life. You are a perfect team. And there is one more many to consider. It doesn't stretch across space but across time. Think about your life. It had a beginning, but the information that makes you is nearly ageless. Inside every one of your cells is that famous molecule, the double helix, your DNA, your deoxyribonucleic acid. This isn't just a set of instructions for building your eyes or your hair. It is a book. It is a history written over 4 billion years. It is an unbroken thread of life passed down from parent to child, stretching all the way back to the very first simple cells that sparked into being in the warm oceans of a young Earth. You are carrying the legacy of every ancestor that ever survived. You hold the resilience of the first creature that learned to swim, the cleverness of the first mammal that hid from predators, the courage of the first human that looked up at the stars and wondered. All that history, all that survival, all that life is inside you. You are not just one person living in this one moment. You are the crest of a 4 billion-year-old wave. You are the current living expression of a story that is as old as life itself. You are the voices of 1,000 generations all singing in the present. So as you rest, let go of the idea that you are just one. It's a heavy burden to carry being a single separate self. Instead, feel the truth. You are a collection of stardust dreaming of the stars. You are a bustling planet home to trillions of lives all working in harmony. You are a river of time carrying the wisdom of all who came before. You are not one, you are many, and in this many you're connected to everything. You're connected to the distant galaxies, to the smallest bacteria, and to the deep unbroken past. You are not alone. You are and have always been a part of it all. You're a beautiful, breathing, thinking chorus. And right now it is time for that chorus to rest. And so as we settle back into this shared space, I want you to think about something small. Something you can hold in your hand. Imagine a single ordinary sheet of paper. It's thin, fragile almost, you kids. You can fold it easily. You fold it once and it's now twice as thick. You fold it again. Now it's 4 times as thick. Then 8. Then 16. After just 7 or 8 folds, the paper is so thick and small that our hands, our physical strength just can't fold it anymore. It's a physical impossibility. But this is a place for thought, not just for hands. What if we could keep folding it? What if we had a machine or some cosmic power that allowed us to just keep folding? Let's follow the journey. We've folded it 10 times. It's about the thickness of a notebook. We fold it 20 times. Now it's about the height of a tall building. Impressive, sure, but it's still here on Earth. This is the point where our minds, our linear minds say, okay, I get it, it gets thick fast. But we don't stop, we keep folding. At 30 folds, our stack of paper has reached the cruising altitude of a jet. We've left the ground. At 40 folds, we are far beyond the orbits of our satellites. We are deep in space. And then we make the 42nd fold. Where are we? How thick is this stack of paper that began as a single fragile sheet? The answer is so massive, so counterintuitive that it feels like a trick. At 42 folds, that piece of paper has reached the moon. It has spanned the dark, cold vacuum of space, all from the simple, quiet act of doubling. This isn't magic, it's mathematics. It is the power of exponential growth. This is perhaps one of the hardest concepts for our minds to truly grasp. Our brains did not evolve to understand it. Our minds are built for a linear world, a walking world. We think if I take one step and then another and then another, I know that in 30 steps I will be 30 steps away. 1 + 1 + 1. It's predictable. It's reliable. It's how we survived. If we throw a spear, we need to know the straight line it will travel. If we are walking to the river, we count the paces. But the universe doesn't always walk, sometimes it leaps. Exponential growth is not 1 + 1 + 1. It is 1 becomes 2, becomes 4, becomes 8, becomes 16. The most important and most deceptive part of this pattern is how it begins. It begins slowly. So slowly, in fact, that it looks boring. For the first few steps, the linear path 1, 2, 3, 4, 5 is actually ahead of the exponential path 1, 2, 4. It doesn't seem like much. And then suddenly something crosses an invisible line. The doubling takes over. The curve, which was almost flat, suddenly turns and races toward the sky faster than we can comprehend. It sneaks up on us because our minds were watching a different kind of race. We see this pattern all around us if we know where to look. Think of technology. For decades, the power of our computers has been doubling roughly every 18 months to 2 years. We call it Moore's Law. At first, it was a curiosity. Computers got a little faster, a little better. We went from calculating numbers to simple games. It was linear, it seemed, and then we crossed the threshold. Suddenly that doubling power exploded. We went from clunky desktops to devices in our pockets that hold the world's entire library of knowledge, that can talk to satellites that can simulate the stars. We carry the power of a Mi-80s supercomputer in our watch. That wasn't an addition, that was a multiplication. This power has a dark side too. A virus is an exponential force. 1 person, then 2, then 4, then 8. For weeks, the numbers seem small, manageable. It's over there, and then before we can even react, the doubling curve goes vertical. It's everywhere all at once. It reveals just how poorly our linear brains are prepared for a doubling world. We see it in our climate. The effects of change are not just adding up, they are often multiplying. A little bit of ice melts. That means less white surface to reflect the sun's heat. That means the ocean absorbs more heat, which in turn melts more ice. That is a feedback loop. That is the universe folding in on itself. We are linear creatures living in an exponential world. It's a profound mismatch. We expect the future to be like the past, just a little bit more. But the power of doubling ensures that the future can be, and often will be, wildly different. It's a lesson in humility. But where did this idea come from? This incredible engine of creation? We only need to look out the window. Nature is the grand master of exponential growth. The universe, it seems, builds its greatest complexities not all at once, but through simple, endlessly repeated rules. Think of a tree, a magnificent, complex, ancient oak. How did it become so vast? It started as a single seed. A trunk grew and then it split. It doubled itself. Those 2 branches in time split again, and again, and again. The rule is simple: divide. The result is a breathtakingly complex canopy, a fractal masterpiece, every leaf a tiny solar collector, all built from one simple repeating instruction. Nature is a fractal. A fractal is a pattern that repeats itself at every scale you look at. Find a fern. Look at the whole frond. Now look at a single leaf branching off it. You'll see that the leaf is a perfect miniature copy of the entire frond. And if you zoom in on a tiny part of that leaf, you'll see the pattern again. It's the same with a river. A great mighty river flows to the sea, and as it meets the ocean, it splits and splits again, creating a delta. A tree turned upside down, carrying water to the ocean. It's in the chambers of a nautilus shell, each new chamber a perfect, slightly larger copy of the one before. It's in the 6-sided perfection of a snowflake, a simple rule of water freezing repeated over and over. Nature doesn't get overwhelmed trying to design the whole complex tree. It just focuses on the next simple fold, the next split. It trusts that the repetition, the accumulation, is all it needs. This is the patience of the universe. It understands that complexity is just simplicity repeated. And this brings this vast cosmic idea right back to us, to our small, quiet lives. We've seen it in paper, we've seen it in technology, we've seen it in the ferns and the trees. What is the lesson for us? It is the philosophy of the fold. There is a simple, powerful truth in that paper folding problem. Folding doesn't just add, it multiplies. We live our lives linearly. We think, I must make a great effort, I must take a giant leap to change my life. We try to go from 0 to 100. And so often we fail because that is not how real lasting growth occurs. We burn out. We give up. But the universe whispers a different secret. It whispers fold. What does that mean in a life? It means understanding that the smallest action when repeated doesn't just add up. It compounds. It multiplies. If you want to learn something new, perhaps to play an instrument or understand the stars, the first day is clumsy. The second day feels just as clumsy. It feels linear. You think, I am just adding one day of practice. But you are not. You are folding your knowledge. The connections in your brain are strengthening, doubling back on themselves. You're not just adding 1 plus 1. You're becoming 2, then 4. And one day you don't just play the notes. You understand the music. You are the music. The change when it comes feels sudden, but it was being built in every tiny patient fold. This applies to our ideas. An idea rarely arrives fully formed. It is a seed. You have a small thought. You fold it by writing it down. You fold it again by telling a friend. They add their thought to it. You fold it again by reading a book that connects to it. Your small idea isn't just +3. It has multiplied. It has connected. It has folded itself into a worldview, a project, a new way of seeing. It's a metaphor for our habits, for our character. A single choice to be patient or to be kind seems small. It seems to vanish. But that choice, when repeated, folds onto itself. It doesn't just add to your life. It multiplies your capacity for peace. That one act of kindness you show someone, it seems to end with that person. But it may have just doubled. It may have changed their state, allowing them to be kind to the next person. It radiates, folding outward in ways we will never ever get to see. This is the power we all hold. It is the opposite of the grand dramatic gesture. It is the power of the small, the quiet, the consistent. We so often overestimate what we can do in one day, and we tragically underestimate what we can do in a year if we just embrace the power of the fold. So as you rest, let go of the pressure to make the giant leap. Let go of the need to fix everything at once. Instead, just think about the next simple fold. The small good thing you can do tomorrow. The one page you can read. The one moment of quiet you can build. The one kind word you can offer. It doesn't feel like it's enough. It feels like a piece of paper. But trust the process. Trust the universe's favorite magic trick. Folding doesn't just add, it multiplies. It is how a single sheet of paper given time can touch the moon, and it is how a single quiet life given patience can touch the infinite. In the humid, tangled undergrowth of a tropical rainforest, an ant is behaving strangely. It is not following the chemical trails of its sisters, not foraging for food, not tending to the colony. Instead, it is walking with a jerky, unnatural gait, compelled by an unseen force. This ant is no longer in control of its own body. It has been hijacked. This is the horrifying and fascinating story of parasitic control, a real-world phenomenon that blurs the line between life, death, and free will. The culprit is a fungus known by the name Ophiocordyceps. Its life begins as a microscopic spore that lands on the ant's body. It drills through the ant's tough outer shell and begins to spread inside, not as a simple infection, but as a puppeteer. The fungus cells multiply, forming a network that weaves throughout the ant's muscles. It doesn't just attack the brain. In fact, it seems to leave the brain itself intact, at least at first. Instead, it acts like a second nervous system, seizing direct control of the ant's limbs. It has, in effect, unplugged the ant's brain from its own body and is now pulling the strings. The ant is a prisoner forced to march. It leaves its colony, its home, and its family forever. Driven by the fungus, it begins to climb. It ascends a plant stem to a very specific height, often around 25 centimeters off the ground. The location is not random. The fungus has a precise environmental goal. It needs a place with the perfect amount of humidity and the ideal temperature, a graveyard that will serve as a launch pad. When the ant reaches this exact spot, the fungus delivers its final command. The ant is forced to lock its powerful jaws onto the central vein on the underside of a leaf. This death bite is permanent. The ant cannot let go. Its muscles are locked in this final fatal embrace. Now immobilized and helpless, the ant starves and dies, but the fungus is just getting started. Protected by the ant's corpse, the fungus continues to grow, feeding on the ant's internal tissues. After a few days, a long slender stalk begins to erupt from the back of the ant's head. This stalk is the fungus's fruiting body. When it is mature, it will rupture, releasing a shower of new spores onto the forest floor below, right onto the path where other unsuspecting ants are foraging. The entire grotesque cycle is ready to begin again. The ant was forced to climb to the perfect location and die in the perfect position, all for the sole purpose of allowing its killer to reproduce. This level of control is shocking, but it is not unique. Nature is filled with similar unsettling examples of parasitic mind control. This is a common survival strategy, and the fungus that attacks ants is just one of many masters of manipulation. Other species of this fungus, for example, do the same thing to flies. The infected fly is driven to climb to a high point, often the top of a blade of grass. It dies there, spreading its wings wide in a final and unnatural pose. This posture ensures that when the fungus erupts from its abdomen, the spores have the widest possible dispersal range carried away on the wind. It's not just fungi either. Consider the parasitic wasp and the orb weaver spider. A female wasp will sting a spider, temporarily paralyzing it. She then lays a single egg on the spider's abdomen. The spider recovers and goes about its business seemingly unharmed. But the larva that hatches from the egg is not a passive passenger. It attaches to the spider and begins to feed, drinking its blood. As the larva grows, it injects powerful chemicals into the spider. These chemicals completely change the spider's behavior. The night before the larva is ready to pupate, it forces the spider to stop building its normal sticky food-catching web. Instead, the spider is compelled to build a completely different structure, a strange, heavy, incredibly strong web designed not to catch flies, but to serve as a durable, protected cocoon hammock for the wasp larva. Once this nursery is complete, the larva has no more use for its host. It delivers a final fatal bite, sucks the spider dry, and then spins its cocoon in the safety of the web the spider was forced to build for it. How is this possible? These parasites are master chemists. They are not acting with conscious intent, but through millions of years of evolution, they have developed the precise chemical compounds that can tap into and exploit the host's nervous system. They are in essence hackers. They find a backdoor in the host's brain or nervous system and inject their own code. They use chemical signals to block some behaviors like fear and to trigger others like climbing or building a strange web. The host is still alive, but its normal behavioral program has been completely overwritten by the parasite's program, which has only one goal: survive and multiply. This phenomenon is disturbing when it happens to insects, but surely we might think more complex animals are immune. This is not the case. The parasitic strategy extends all the way to mammals, and it gets uncomfortably close to home. There is a single-celled parasite called Toxoplasma gondii. It is one of the most successful parasites on Earth. Its life cycle is complex, but its ultimate goal is to reproduce, and it can only do this inside the gut of a cat. But how does a microscopic organism living in, say, a rat get itself into the stomach of a cat? The answer is by hacking the rat's brain. A normal, healthy rat is instinctively, powerfully afraid of cats. The smell of cat urine is a red alert signal that causes immediate panic and hiding. This is a fundamental survival instinct. When a rat becomes infected with toxoplasma, the parasite forms tiny cysts in its brain, and these cysts go to work on the rat's behavior. The parasite doesn't just make the rat less afraid of cats, that wouldn't be efficient enough. Instead, it performs a terrifying reversal. It rewires the rat's brain so that the smell of cat urine is no longer frightening. It actually becomes attractive. The infected rat is drawn to the smell of its number one predator. This, of course, is a death sentence for the rat. It will be curious, not cautious, and will be easily caught and eaten. For the parasite, it is mission accomplished. It has successfully chauffeured itself from its intermediate host into the gut of its final host, the cat, where it can finally reproduce. It sacrificed the rat's life by surgically removing its most essential survival instinct. This brings us to the final and most profound question. This parasite Toxoplasma gondii doesn't only infect rats, it infects a huge range of warm-blooded animals, including humans. It is estimated that as much as 1/3 of the entire human population, billions of people, is infected with Toxoplasma. For most of us, our immune systems are strong enough to keep the parasite in a dormant cystic state, and it causes no immediate illness. But knowing what it does to the brain of a rat, researchers have begun to ask a chilling question. Is it really doing nothing to us? The evidence is not yet conclusive, but it is deeply suggestive. Studies have found correlations, not proven causes, but statistical links between toxoplasma infection and subtle changes in human behaviour. Infected individuals, for example, have been found to be slightly more prone to risk-taking. Some studies have shown they are more likely to be involved in traffic accidents as they may have slightly slower reaction times or a more impulsive nature. Other research has suggested links between the infection and personality shifts, or even a higher risk for developing serious mental health conditions like schizophrenia or anxiety disorders. This research is still in its early days and it's incredibly difficult to separate cause from effect. But the mere possibility raises a question that strikes at the very heart of our identity. If a microscopic organism, a tiny stowaway in our brain, can nudge our personality, influence our moods, or make us just a little more reckless, how much of our behaviour is truly our own? It forces us to ask, are we really in control of ourselves? This is the ultimate lesson of the parasitic world. Nature does not operate on a system of good or evil, fairness or cruelty. It is a cold, methodical, relentless algorithm. This algorithm's only function is to find out what works for survival and replication. The fungus that drives an ant to its death, the larva that enslaves a spider, the parasite that makes a rat love its killer, these are not evil. They are simply strategies that worked. They are solutions that were found and kept by millions of years of ruthless natural selection. This algorithm does not care about what we call free will. It does not care about consciousness or fear or love or the ant's loyalty to its colony. It only cares about the transmission of genetic information. We as humans like to see ourselves as separate from this raw biological process. We believe we are thinkers, individuals, and masters of our own destiny. But these parasites are a stark reminder that we are biological machines too. We are running on complex neurological software, and in the vast cold operating system of nature, we are just as vulnerable to being hacked as any other creature. We have journeyed so far out beyond our world, past the boundaries of our solar system, and into the silent, endless night of the galaxies. We've looked at the grand, sweeping architecture of the cosmos, the invisible forces of dark energy and the fiery birth of stars. But now let's take a different kind of journey. Not outward, but inward. Let's travel into a universe that is just as vast, just as mysterious, and just as magnificent. The universe inside a single one of your cells. As you rest here breathing softly, you are an ecosystem. You're a walking, thinking, feeling galaxy of trillions of cells all working in harmony. And inside the nucleus of almost every one of those cells is the instruction manual, the blueprint, the soft spiraling ladder of deoxyribonucleic acid, your DNA. We hold this code so close we think of it as us. It's the code that makes your eyes the colour they are, that defines your smile, that built the very brain you're using to hear these words. It is your unique signature separating you from everyone else. And yet the most profound secret of this code is not how it separates us, but how it connects us. Prepare yourself for a fact that sounds like a riddle. You, right now, share about 50% of your fundamental genetic code with a banana. Yes, a banana. That simple yellow fruit. It feels impossible, doesn't it? You have a brain, a heart, you have thoughts and dreams. A banana is a plant. But this startling truth reveals one of the deepest realities of life on Earth. That 50% similarity isn't in the parts that make us human, it's in the parts that make us alive. Deep in our code and in the banana's code are ancient instructions. They are what scientists call conserved genes. You can think of them as the original housekeeping files for the machinery of life. These are the genes that tell a cell how to breathe, how to process sugar for energy, how to divide, how to repair itself. These are the most basic fundamental instructions for being a living thing on planet Earth. Our planet's life isn't a collection of separate walled-off kingdoms. It is one single enormous sprawling family tree. Every living thing you meet, the bird outside your window, the ancient redwood tree, the mushroom in the forest and the banana on your counter. We all share a common ancestor. We all began from the same humble spark of life billions of years ago. We are all just different branches growing in different directions from that same ancient trunk. The banana is a very distant cousin, but it is still family. This web of connection grows even tighter when we look closer to home. Think of another human being, someone you love, someone you pass on the street. You and that person, despite all your wonderful differences in appearance, thought and talent, are 99.9% genetically identical. Let that sink in. All of human history, all the art and music, all the languages and cultures, all the conflict and all the love, all of it is the product of a tiny, tiny difference, just 0.1% of our code. The rest, 99.9% is just human. We are in our very essence almost entirely the same, and we can step even closer. Our nearest living relative in the animal kingdom is the chimpanzee. When we compare our blueprint to theirs, we are 98.8% the same. Think about that. Everything we believe makes us human. Our sprawling cities, our poetry, our philosophy. Our ability to look up at the stars and wonder why all of that complexity is contained in a sliver of code that is just 1.2% different. It's a truly humbling thought. It makes you wonder if we overestimate our differences and underestimate the profound shared experience of the other 98.8%. The part that is simply about being alive, breathing, forming bonds, and navigating the world. The mystery of what makes us us is hidden in that tiny biological whisper of difference. But our code isn't just a simple, clean blueprint. It's an ancient living document. It's a diary. It carries the echoes of a deep and wild past. If you were to read your own genetic script from end to end, you would find that it's not all human. Scientists have discovered that roughly 8% of your total DNA is not from your human ancestors at all. It is the leftover dormant code of ancient viruses. Millions of years ago, these viruses infected our distant ancestors. And like biological graffiti, they wrote their own code into our family line. They became part of us. We are quite literally a mosaic. We are a living archive of our planet's history, carrying the ghosts of ancient plagues and forgotten infections within every cell of our body. So what are you? You are not a single separate thing. You are a collection. You are a symphony. You are a collaboration. You are 50% ancient life subserving the basic machinery of existence with a banana. You are 98.8% primate sharing the breath and blood of the living world. You are 99.9% human, a near-perfect echo of everyone around you. And you are 8% ancient virus, a living record of the deep past. And all of it, the human, the chimp, the banana, the virus, every living thing we have ever discovered, from the smallest bacteria in the deepest ocean trench to the largest whale, all of it is written in the exact same simple 4-letter alphabet. Adenine, thymine, cytosine, guanine. Just 4 letters, a T, C and G. That's it. The entire library of life on Earth. The same 4-letter code, just arranged in different beautiful and complex orders. You are not just living in the universe is living in you. You are a breathing, thinking, feeling piece of the cosmos looking back at itself. And you are written in the same language as everything else that is and ever was alive. Just breathe. For as long as we have known of them, black holes have been the symbol of permanence. The ultimate end, a cosmic prison from which nothing, not even light, can return. We saw them as the universe's final punctuation mark. A one-way street to infinity. But this idea, this deeply held belief in forever, was about to be challenged. It was challenged not by a great astronomer looking through a new telescope, but by a brilliant mind looking at the strange, fuzzy and magical rules of the quantum world. In the 1970s, Stephen Hawking was thinking about black holes. But he was thinking about them in a way no one else had. He was trying to combine the physics of the very big gravity with the physics of the very small quantum mechanics. And what he found turned our understanding of reality upside down. He made a shocking discovery: black holes are not completely black. They must, according to the math, have a temperature. And if something has a temperature, it must radiate energy. It must glow. It's an impossibly faint glow, far too cold and weak for us to ever see, but it is there. This faint theoretical energy leaking from the edge of a black hole is now known as Hawking radiation. This discovery means that black holes are not static, eternal objects. They are active. They are slowly, almost imperceptibly losing energy. They are losing the mass. But how? How can anything escape that inescapable pull? The secret doesn't come from inside the black hole. Nothing escapes from inside the event horizon. The secret, it turns out, is in the empty space right at the very edge. You see, in the quantum world, empty space is not empty at all. We call it the quantum foam. It is a chaotic, bubbling soup of potential. Out of this nothingness, pairs of virtual particles are constantly popping into existence. A particle and its opposite, an antiparticle. In normal space, these two partners pop into being, see each other almost instantly, and then annihilate, disappearing back into the foam. Their existence is unimaginably brief. But now imagine this happening right on the razor's edge of an event horizon. A pair of virtual particles pops into existence, but this time they are separated by that ultimate boundary. One particle forms just inside the event horizon and its partner forms just outside. The one inside is immediately captured. It is pulled into the singularity, lost forever. But the particle outside is now alone. Its partner is gone. It cannot annihilate. It has no one to dance with. So it is promoted from a virtual particle to a real particle. It is now free, and it flies away from the black hole out into the cosmos. If you were watching from a safe distance, you would see a tiny particle of energy just appear to stream away from the black hole. It would look exactly like the black hole was glowing or emitting radiation. But here is the crucial question. Where did the energy to create that real particle come from? It cannot be created from nothing. That would break the most fundamental laws of physics. The energy has to be paid for. The answer is that the black hole itself pays the bill. The energy is stolen in a way from the black hole's own gravitational field from its own mass. The particle that fell in actually contributes negative energy to the black hole, which is a complex way of saying that the black hole's total mass goes down by a tiny amount. Think of it like a tiny slow leak. One particle at a time, the black hole is paying an energy tax to the universe. And if a black hole is constantly leaking mass particle by particle, what is the ultimate consequence? It means it is shrinking. This process is called black hole evaporation. Now, this is not something we will ever see. The process is so incredibly slow that it's almost meaningless in human terms. For a black hole just the mass of our sun, it would take 10 to the power of 67 years to evaporate. That number is so large, the current age of the universe, 13.8 billion years, is like a single grain of sand compared to all the beaches on Earth. But if you can wait long enough, any black hole, no matter how big, it will eventually radiate away its mass. As it gets smaller, the radiation actually gets stronger. It gets hotter. In its very final moments, a black hole that has existed for eons will shrink down to the size of a mountain, then a house, then an atom, and in the last final fraction of a second, it will explode in a brilliant blinding flash of high-energy gamma rays, returning all of its borrowed mass and energy back to the universe. This changes everything. It means that even the monsters of the cosmos, the objects we thought were the very definition of the end, are also temporary. It tells us that permanence is an illusion, nothing lasts forever. But this discovery, as beautiful as it is, solved one problem and created a much bigger one. It's a problem so deep it threatens the very foundation of physics. We call it the information paradox. Here is the rule. In our universe, information can never be destroyed. When we say information, we don't just mean the words in a book. In physics, information is the unique, specific quantum recipe for every single particle. It's the blueprint that makes you and a star a star. If you burn a book, you might think the information is lost, but it's not, it's just scrambled. If you could theoretically track every single particle of smoke, every bit of ash, and every photon of heat released, you could reconstruct the book. The information is still there, just spread out. So here is the paradox. What happens when you throw that book into a black hole? The information, the recipe for the book, falls past the event horizon. It's trapped. Then you wait. You wait for trillions upon trillions of years, and the black hole evaporates. It disappears in that final flash of light. The radiation that came out, the Hawking radiation, seems to be random. It's thermal radiation. It's just generic heat. It does not seem to contain any of the scrambled information for the book. So, where did the book's information go? The black hole is gone. The radiation that's left is blank. Did the universe just delete the blueprint for the book? If it did, then one of the pillars of modern science is wrong. This is the crisis. Scientists have been arguing about this for decades. There are three main ideas. One idea is that the information is truly lost. This is what Hawking first believed. He suggested that when a black hole evaporates, it takes the information with it, permanently deleting it from reality. This would mean we need to find a new, deeper theory of physics. Another idea is that the information is encoded in the radiation. Maybe the radiation only looks random, but it's actually incredibly scrambled, just like the smoke from the burned book. If we had a powerful enough quantum computer, we could decode the radiation and find the recipe for the book inside it. The third and perhaps strangest idea is called the holographic principle. This theory suggests that the information never truly falls into the black hole at all. It suggests that all the information for everything the black hole has ever swallowed is smeared or stored on the two-dimensional surface of the event horizon like data on a vast cosmic hard drive. In this view, as the black hole evaporates and the event horizon shrinks, that information is slowly released back into the universe encoded in the escaping radiation. It implies that the three-dimensional reality we see might just be a projection, a hologram of information stored on a distant 2D surface. We still don't know the answer. Black holes are the ultimate laboratory because they are the one place where the two great theories of our universe collide. You have Einstein's general relativity, the theory of the very big of gravity, and the warping of space-time. And you have quantum mechanics, the theory of the very small of particles, probability, and foam. These two theories are both correct, but they do not speak the same language. They break down when they try to describe the center of a black hole or the edge of the event horizon. To solve the information paradox, we will need to find a single beautiful theory that unites them, a theory of everything. These dark objects, once thought to be simple dead ends, have become the greatest puzzle in all of physics. They are the key, and they have taught us the most profound lesson of all. Even the deepest, most absolute darkness is not final. Even the shadows are temporary. In the end, everything is borrowed and everything must be returned to the light. There is a fundamental rule to the universe that changes how we see everything. Light does not travel instantly. It is incredibly fast, faster than anything else we know, but the universe is overwhelmingly vast. Because of this, light takes time to journey across space. This simple fact transforms the night sky into the most profound time machine we have ever known. When we look up, we are not seeing things as they are now. We are seeing a collection of thens. The familiar moon we see is not the moon of this exact second, but the moon as it was just over a second ago. The sunlight that warms our face left the sun 8 minutes before it reached us. These are small delays, but as we look deeper into space, the delays become staggering. The very nearest star to us, Proxima Centauri, is so far away that its light takes over 4 years to reach Earth. If you find that star in the sky tonight, you are seeing the light that left it 4 years ago. You are seeing that star as it was when the world was a different place. When we look at the beautiful hazy patch of the Orion Nebula, a stellar nursery where new stars are being born, we are seeing light that has travelled for over 1,000 years. That light began its journey to our eyes when Earth was in its medieval period, long before the invention of the telescope that we now use to see it. Every single point of light in the night sky is a message from the past. This time delay means that our view of the universe is inherently incomplete, because the universe itself has a finite age, about 13.8 billion years. We can only see the things whose light has had enough time to reach us since the beginning. This creates a boundary, a cosmic horizon. It is not a physical wall, but a horizon in time. There is almost certainly more universe beyond this horizon, but the light from those distant regions simply has not had the time to complete its long journey to us. We are enclosed within a bubble of the observable universe. Even more profoundly, this delay creates what we could call a sky of ghosts. The light from a star that is, for example, 500 light years away is showing us how that star looked 500 years ago. But what happened to the star during those 500 years? For most stars, they continue to shine steadily. But some massive, brilliant stars live fast and die young. It is a statistical certainty that many of the stars we see twinkling in the night sky are in reality already dead. They may have exploded in a supernova or collapsed into a black hole centuries or millennia ago, but their final light has not yet reached us. We look up and see a beautiful shining star, but we are only seeing its phantom, the light it emitted, long before its death, still travelling through space. This relationship with the past is not a one-way street. Just as we receive ancient light from the cosmos, we are sending our own signals out. Since the invention of radio and television, Earth has been unintentionally broadcasting signals into the void, travelling at the speed of light. These signals are our own electronic ghosts, carrying our music, our news, our conflicts, and our greetings. Our earliest strong broadcasts have now travelled dozens of light years away, washing over any planets that might be orbiting those nearby stars. An alien civilization 80 light years away, if it had a powerful enough receiver, would not know about our modern world. They would be receiving our very first television signals. Just as we review the universe's past, the universe is in its own way reviewing ours. We are a part of this great cosmic exchange where now is a local event and the past is what is shared across the distances. If we can look back 1,000 years, or 1,000,000 or 1,000,000,000, what is the farthest back we can possibly see? What is the oldest light? We can look past galaxies and quasars to a time before any stars or galaxies existed. For the first 380,000 years after the Big Bang, the universe was not transparent. It was a hot, dense, foggy soup of particles and energy. Light was trapped, bouncing around constantly. Then, at about 380,000 years, the universe cooled down enough for the fog to clear. Atoms formed, and the universe suddenly became transparent. The light that existed at that exact moment was finally set free, and it has been streaming across the cosmos ever since. We can still detect this light today. The expansion of the universe has stretched this light so it is no longer visible, but we see it as a faint glow of microwaves in every direction we look. This is the cosmic microwave background. It is quite literally the baby picture of the universe. It is the afterglow of creation, the oldest and most ancient light we will ever be able to observe. All of this tells us that light is far more than just illumination. Light is memory. It is the universe's hard drive carrying the information of everything that has ever happened. Because of the time it takes for light to travel, the universe does not forget immediately. The past is not erased. It is simply travelling away. To be an astronomer is to be an archaeologist of time itself. So what are we? If we live in this vast universe of ghosts, echoes, and ancient light, what is our place in it? When we bring all these pieces together from the cosmic to the microscopic, a beautiful synthesis appears. In the end, we are patterns of stardust. The very iron in our blood, the calcium in our bones, and the oxygen we breathe were not created in the Big Bang. They were forged in the intensely hot centres of massive stars that lived, died, and exploded billions of years ago, scattering these elements across space. We are in the most literal sense made of the ashes of long-dead stars. We are also minds shaped by microbes. We are not solitary individuals, but walking ecosystems, our bodies home to trillions of bacteria that are essential to our survival. They help us digest our food, protect us from disease, and as we are learning, may even influence our thoughts and moods. We are a collaboration between our human cells and this ancient microscopic life. And finally, we are time-bound creatures observing ancient light. Our own lives are tragically short, a fleeting moment on a small rocky planet. We are bound by seconds and years. And yet through the power of our minds and our instruments, we have found a way to look beyond our now. We use the ghost light from the distant past to understand the very cosmic processes that created us. In a very real way, we are the universe's way of becoming aware of itself. We are the creatures who fold the universe. We use the abstract and beautiful language of mathematics to find the patterns in the chaos, to describe the curve of space and the behavior of light with simple equations. We are the creatures who wonder. We look at the cosmic echoes and the stardust we are made from, and we ask, why? And what else is out there? This relentless curiosity is what drives us forward, and we are the creatures who connect. We are biologically connected to every living thing on our planet and cosmically connected to the stars that died to give us life. The universe speaks to us. It does not use words, but it speaks in the language of atoms and the physics that binds them. It speaks in the echoes of light from the beginning of time. We stand in the middle of this incomprehensible vastness on a small world looking at the ghosts of the past. We will never understand all of it. But the miracle is that we understand anything at all. We understand just enough to know how much more there is to learn. And that is perhaps the most important thing. We are the part of the universe that can continue to ask questions.